In this video, we are going to continue talking about the topics of Chapter 7. Now we are going to focus on dietary lipids and trans fat. When it comes to the substances that we have been looking at, lipids are an important family of biomolecules that exist in the human body and in other organisms. Lipids are going to be divided into two large families known as fatty acids and steroids. The fatty acid family subdivides into other groups that includes waxes, triacylglycerols, glycerophospholipids, and sphingolipids. Why are lipids important? Well, these biomolecules are actually important features of cell membranes, fat-soluble vitamins, and steroid hormones. Steroid hormones are actually biomolecules that are important in the development of the human body. It is important to note that when it comes to lipids, these molecules are soluble in organic solvents, but not in water. So this suggests that these molecules are overall nonpolar. When it comes to fatty acids specifically, it is important to note that fatty acids can be classified as saturated or unsaturated. And the following two tables are actually going to show us specific examples for fatty acids. As we can see here, saturated fatty acids are going to be fatty acids due to the fact that these molecules are going to have a series of carbon, carbon, and carbon hydrogen single bonds. And we can see it at the tail of the molecules. These molecules are called fatty acids because they contain a carboxylic acid in its structure. And this carboxylic acid, I'm going to highlight it at least in one of the molecules. We could see it right here, C double bond O, OH. That's what symbolizes the carboxylic acid. Now, in this table, we have the name of some common saturated fatty acids, which include lauric acid, which you can see that is present in coconut oil, myristic acid, which has 14 carbons in length and is found in nutmeg. We have palmitic acid, which is present in palm oil, and it has 16 carbons. And lastly, we have stearic acid, which is one of the fatty acids that is mainly found in animal fat, which has 18 carbons. Each of these fatty acids, in their characteristics, in their structure, we can observe that the carbon-carbon and carbon-hydrogen bonds are single bonds. When it comes to unsaturated fatty acids, it's important to note that these molecules are called unsaturated fatty acids because when we look at the carbon-carbon and carbon-hydrogen bonds, they contain at least one or more carbon-carbon double bonds. And if a fatty acid only has one carbon-carbon double bond, that is known as monounsaturated fatty acid, as we can see here. And the two examples that we have of monounsaturated fatty acids are palmitoleic acid, which contains 16 carbons and one double bond. Then we have oleic acid, which has 18 carbons and one carbon-carbon double bond. And then we can have polyunsaturated fatty acids. These include linoleic acid, which also has 18 carbons, but it has two carbon-carbon double bonds. We have linolenic acid, which has 18 carbons and three double bonds. And lastly, we have arachidonic acid, which has 20 carbons and 4 carbon-carbon double bonds. There's a few features that I want to explain about unsaturated fatty acids. One of which is that when we look closely at the conformation of those carbon-carbon double bonds, these fatty acids, as we can see, and we can find them in nature, have a cis conformation at the carbon-carbon double bond. And you can see it, all of these unsaturated fatty acids have a cis conformation on that carbon-carbon double bond. So what this suggests is that in nature, that is the preferred structure for unsaturated fatty acids. Another thing that I want to point out when it comes to unsaturated fatty acids is that we can find, quote unquote, its omega term. In everyday life, maybe when you buy certain vegetable oils, you may see that the labels say, oh, this oil has omega-3, omega-6, omega-9. And that has been actually linked to the way that healthy fats have specific structures in them. And the more omegas you have in a particular structure, the healthier is thought to be the oil, because one of the things is that unsaturated fatty acids are hard to be synthesized by the human body. So we need to consume them because they are specifically important in cell membranes. So how do we determine the omega term in a particular fatty acid? To do this, I'm going to utilize specifically oleic acid as an example. In oleic acid, the first thing in order to determine the omega term that it has is that you're going to number the carbon atoms in your fatty acid starting from the end that is opposite from the carboxylic acid. So what that means is that I'm going to number that unsaturated fatty acid starting here. This is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Those are the 18 carbons in oleic acid. Now, we can see that the first carbon in the carbon-carbon double bond is carbon 9. So whenever we talk about oleic acid, or we see it in its oil form as a triacylglycerol in the form of olive oil, we say that that product actually has or it is, I should say, an omega 9 fatty acid, or in the case of oil, is an oil that has omega 9 structures. You can use as an example or practice at home with palmitoleic acid or with any of the other ones. So if a molecule has multiple double bonds, for example, like in linoleic acid, let me number the carbons. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Those are the 18 carbons in the molecule. So for example, for linoleic acid, you will say that this fatty acid has, specifically in terms of its omega term, omega 6 and omega 9 fatty acids. So now that we understand at least what is a saturated fatty acid, what is an unsaturated fatty acid, and we have looked at some of its properties, let's define what is a fat versus what is an oil. Fats and oils are defined by the source where they come from. Fats, which are usually solid at room temperature, are defined because they are coming from animal sources. So, whatever we see in meat, we call it fat. Whole milk has fat, butter has fat, cheese has fat. And again, the reason why we call it fats is because it's coming from animal sources. On the other hand, whenever we define an oil, oils are going to be liquid at room temperature, and they are going to be obtained from plant sources. So, for example, if you look at a jar of palm oil or coconut oil, which those are among the oils that are semi-solids at room temperature, we call them oils and not fat because they come from plant sources. In order for us to understand how specifically in some structures we have fats and oils that are going to be specifically having different states of matter, we need to look at the percent of saturated and unsaturated fatty acids in these fats and oils. As you can see in the red lettering, vegetable oils have low melting points because they have a higher percentage of unsaturated fatty acids compared to animal fats. Now, if we read the following bar graph table, or bar graph, I should say, it's not a table, it's just a bar graph, we can see that we have two states of matter represented. We have the substances, specifically, that are found as solids. And then we have the substances that are found as liquids. Notice that coconut is the only one that it is from a plant source that usually we find it as a solid at room temperature. Now, what does beef tallow, butter, and coconut oil have in common? Well, first of all, they are going to have the same state of matter at room temperature, which is going to be solid. But in addition to that, we can see that when we look at them in the molecular level, the reason why they have this particular state of matter is because the amount of saturated fat that they have is very large when we look at the other components that are there. So we can observe that a specific fatty acid present in the molecule, in other words, the saturated fatty acids that are in these structures, are actually defining how we are going to see something in terms of their state of matter. If now we move on to the liquids, and we can see that they're all plant sources: olive, canola, soybean, sunflower, safflower, corn. All of these, which are found as liquids at room temperature, have a particular feature in them, and that is that they're going to have more monounsaturated and polyunsaturated fatty acids in them. And we can see that by looking at the bar graphs on each of these substances. So, as you can see, the fatty acids present in fats and oils affect not only their state of matters, but they will affect their melting points. And in the next slide, we're going to see a specific example. So let's explore the following example. Here, we are going to explore what is going to be the difference between melting points of saturated and unsaturated fatty acids. Let's take, for example, the following two fatty acids. On the left, we have stearic acid. Stearic acid is a saturated fatty acid that has 18 carbons in length. On the right side, we have oleic acid, which is an unsaturated fatty acid that is also 18 carbons in length. So the only difference between these two substances is that the one on the left, stearic acid, has no carbon-carbon double bonds, and the one on the right, which is oleic acid, has one carbon-carbon double bond. If we look closely at the melting point of each of these, we can see that stearic acid has a melting point of 69 degrees Celsius, while oleic acid has a melting point of 14 degrees Celsius. So they have very different melting points. We can observe that on saturated fatty acids, we have a lower melting point compared to saturated. But why is that? Well, we can actually explain it by understanding attractive forces. That is, when we look at these two molecules, essentially both molecules are going to have dispersion forces as their strongest attractive force. Now, if they both have the same attractive force, why are they so different? It is known that specifically saturated fatty acids have the ability, because their tails have that extended form, they are able to stack onto one another. To use an analogy, you can actually think that saturated fatty acids are going to be stackable, similar to Pringle potato chips. And having this ability to stack is actually going to increase the amount of dispersion forces that all the molecules can experience. On the other hand, for oleic acid, when it comes to the structure, we can actually see that that double bond creates what we call overall a kink in the molecule. So it actually bends the molecule in such a way that then these molecules that are unsaturated, when you try to stack them, having that kink or that bending within the structure, what it does in turn is to enable them to stack to a great degree. So when we use an analogy in order to think of the stackability of unsaturated fatty acid, you can actually think about that in terms of Lay's potato chips. They can stack, but not as well as Pringle potato chips. And remember that this is due to the surface area difference that saturated fatty acids will have compared to unsaturated fatty acids.